Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on group, lecture number 41, in which I will discuss on conjugate of a subgroup by an element of a group. Now we define conjugate of a subgroup H by an element A of a group G. Let G be a group and H be subgroup of G. Let small a be an element of G. Then we get A H A inverse equal to A H A inverse such that H belongs to subgroup H. Then this set is called the conjugate of H by the element A. Now I will give an example. Let G be a group which is equal to symmetric group of degree 3 and H is a subgroup of S3 containing elements row 0 and row 3. Now we find conjugate of H with respect to elements of G, that is elements of S3. Elements of S3 be row 0, row 1, row 2, row 3, row 4, row 5. Each of the element of S3 be permutation defined on set S containing elements 1, 2, 3. Row 0 be the identity permutation and row 1, row 2 are permutations of 3 cycle. Row 3, row 4, row 5 are permutations of 2 cycle. Now we find the conjugate of H with respect to these elements one by one. First we take element row 0. Row 0 H, row 0 inverse. Since H contains row 0 and row 3, so firstly we take row 0, row 0, row 0 inverse. Secondly we take row 0, row 3, row 0 inverse. Here row 0 be the identity permutation, so inverse of row 0 will be row 0. So here we get row 0, row 0, row 0, that is row 0. Here row 0, row 3, row 0, that is row 3. Therefore the conjugate of H with respect to row 0 be a set containing elements row 0 and row 3, which is equal to H. Now we want to get the conjugate of H with respect to element row 1. So row 1 H, row 1 inverse. So firstly we take element of H row 0. So here row 1, row 0, row 1 inverse. Then we take element of H row 3. Row 1, row 3, row 1 inverse. Since row 1 inverse is row 2, so here we write row 2, here we also write row 2. This is the identity permutation row 0. So here we will get row 1, row 2. Here row 3, row 2 by composition gives row 5, and row 1, row 2 be row 0, and row 1, row 5 equal to row 4. Therefore, conjugate of H with respect to element row 1 is a set containing elements row 0 and row 4. Let name of this set is K. Similarly, we may find conjugate of subgroup H with respect to element row 2, and we will get set containing elements row 0, row 5. Let this is L. Then we find conjugate of H with respect to element row 3, and we get a set containing element row 0 and row 3. This is equal to H. Similarly, we may find the conjugate of H with respect to element row 4, and this is equal to a set containing elements row 0 and row 5. This is equal to L. Then we find conjugate of H with respect to element row 5, and we get a set containing element row 0 and row 4. This is equal to K. Therefore, we get three subgroups H, K, L, which are conjugate to subgroup H. We have mentioned here that three subgroups H, K and L. Here we have seen that H, K, L are three sets. H is a subgroup, but we do not know that K and L are subgroups or not. Now we prove that the conjugate of a subgroup is a subgroup. Now we shall prove a theorem. Let H be a subgroup of a group G and A belongs to G. Then the subset A inverse containing elements of type A, small h, A inverse, small h belongs to capital H, is a subgroup of G. Now we prove this. Given that G be a group, and H be a subgroup of G, let A be an element of G. Then A inverse equal to A inverse such that H, small h belongs to capital H. Let P belongs to A inverse implies that P will be an element of type H1 A inverse for some H1 belongs to capital H. Let Q be another element of A inverse implies that Q equal to A H2 A inverse. H2 be some elements of H. Now P operation Q equal to A H1 A inverse operation A H2 A inverse. By associative property, A H1 A inverse A H2 A inverse. This is equal to A H1. This is identity element A inverse A. H2 A inverse. This is equal to A H1 and here H2. H1 and identity element becomes H1 and A inverse. Let this is number 1. Since H is a subgroup of G, therefore H1 H2 belongs to H, implies that H1 H2 belongs to H by closure property. Let H1 H2 equal to H3 belongs to H. Let this is number 2. From 1 and 2, PQ equal to A H3 A inverse. This means this belong to A H A inverse. Since H3 belongs to H, therefore PQ belongs to A H A inverse, implies that P operation Q belongs to A H A inverse. That this is number 3. Again, P equal to A H1 A inverse. Now P inverse equal to A H1 A inverse whole inverse, and this equal to A inverse whole inverse H1 inverse A inverse, and this equal to A inverse of inverse equal to A H1 inverse A inverse. Since H1 belongs to capital H and capital H is a subgroup of G, therefore each element of capital H must have an inverse. Therefore H1 inverse belongs to H. This means P inverse equal to A H1 inverse A inverse belongs to A capital H A inverse. From 3 and 4 we get PQ belongs to AH A inverse, implies that P operation Q belongs to AH A inverse, and P belongs to AH A inverse implies that P inverse belongs to AH A inverse. Therefore AH A inverse is a subgroup of G. Proved. Now we prove a theorem. Theorem is a subgroup H of a group G is normal if and only if A H A inverse equal to H. for every A belongs to G, that is H is a self-conjugate subgroup. Now we prove this. Let G be a group and H be a subgroup of G. Firstly, we consider H is a normal subgroup of G. Therefore, AH equal to HA for all A belongs to G. This is number 1. Now let P belongs to AH A inverse. Therefore, structure of P will be of the form A H1 A inverse. For some H1 belongs to capital H. Implies that PA equal to A H1 A inverse A. Implies that PA equal to A H1 A inverse A is identity element. Implies that PA equal to A H1. Since A capital H equal to capital H A, that means elements of AH and elements of HA are same. Here we see that AH1 belongs to AH. So we may get same element in HA. Let the same element be H2A in HA. Since AH equal to HA, implies that P A inverse equal to H2 A inverse. This equal to H2 identity element equal to H2 belongs to H. And in left side, P identity element means P equal to H2 belongs to H. Here this is number 2 and this is number 3. From 2 we see that P belongs to AH A inverse, and in 3 we get P belongs to H. That means AH A inverse is subset of H. Let this is number 4. Again, let Q belongs to H. Implies that QA belongs to HA. Therefore, QA will be of the form H3A. Since HA equal to AH, therefore we may write this as AH4, because this element in HA must be equal to an element in AH. That element is AH4. Since HA equal to AH, implies that QA inverse equal to AH4 A inverse. Implies that QA inverse is identity element. this equal to A H4 A inverse implies that Q equal to A H4 A inverse. This belongs to A capital H A inverse, since H4 belongs to capital H. Let this is number 5 and this is number 6. From 5 and 6 we get that H is subset of AH A inverse. This is number 7. Therefore, from 4 and 7 we get AH A inverse equal to H. This is 8. Since we have assumed that H is a normal subgroup of G such that AH equal to HA, and we get the result that AH A inverse equal to H. Therefore, if H is a normal subgroup of G, then H is self-conjugate. Conversely, let AH A inverse equal to H for all A belongs to G. Now we have to show that H is a normal subgroup of G, that is left coset equal to right coset. Let P belongs to AH implies that P equal to A H1 implies that P equal to A H1 E identity element. We may write this A H1 A inverse A H1 A inverse under bracket A. Since here we see that AH A inverse equal to H, that means this element belongs to AH A inverse, and this will be equal to an element of H, capital H. Let that element is H2 A, and H2 belongs to capital H. Therefore, H2A belongs to HA. Hence, from here we get that P belongs to AH, and here we get P belongs to HA. Therefore, AH is subset of HA. Again, let Q belongs to HA implies that Q equal to, let H3A. H3 belongs to capital H. We may write this identity element H3A. Identity element is A inverse H3A. We may also write this A inverse H3 A inverse whole inverse means A. Since A inverse belongs to G and A inverse also belong to G, therefore A inverse H3 A inverse whole inverse belongs to AH A inverse. Since A belongs to G, for all A belongs to G, here in place of A we have A inverse, and AH A inverse equal to H. That means this element must belong to capital H. Let that is H4, this is equal to H4, and AH4 belongs to A capital H. Therefore Q belongs to HA implies that Q belongs to AH. Hence HA is subset of AH. Here we have seen that AH is subset of HA, and here we get that HA is subset of AH. Therefore we get AH equal to HA. Therefore left coset of H equal to right coset of H for all A belongs to G. Therefore H is a normal subgroup of G. Proved. Now we prove a problem. Prove that center ZG of a group G is self-conjugate subgroup of G. Now we prove this. Let G be a group and ZG be the center of group. Then ZG contains all those elements H of G such that AH equal to HA for all A belongs to G. Therefore, if H belongs to ZG implies that AH equal to HA for all A belongs to G. Implies that AH A inverse equal to HA A inverse. Implies that AH A inverse equal to HE. Implies that AH A inverse equal to H. Since H is arbitrary element of ZG, therefore here this is true for all H belongs to ZG. Therefore A ZG A inverse equal to ZG. Therefore ZG is self-conjugate subgroup of G. Proved. Now I will give you details of my lecture notes. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.